If you load a wooden shelf with massive encyclopedias on the right side, leaving the left completely empty, the wood eventually bows and cracks. Numbers in the real world do the exact same thing. They rarely stack up evenly. Instead, they pile heavily onto one side. When we face a massive spreadsheet of these numbers, our instinct is usually to ask for the average. We want a single, clean number to tell us what a typical row looks like. But if those numbers are stacked heavily to one side, that standard average will lie to you about what is actually normal. Trusting that a dataset is neatly balanced without checking its physical shape first is the fastest way to misread reality. Because of that risk, data scientists rarely ask for the average right away. They start by visualizing the data to diagnose its actual condition. In Python, you can use a diagnostic tool by typing df.hist. This plots out the exact frequency of every single data point in your set. This is a chart showing the frequency of housing prices in California. Right away, you can see this massive peak on the far left side. That represents the vast majority of standard everyday homes. But trailing off of that peak is a thin line of data that stretches far out to the right side, representing a tiny fraction of ultra-expensive properties. Statisticians have a formal term for this exact lopsided shape, a right-skewed distribution. We can measure exactly how severe this asymmetry is by typing df.skew, which returns a specific number telling us how far the data leans away from perfect balance. That massive cluster on the left side of our chart translates directly into dense, tightly packed rows of identical suburban homes. Meanwhile, that thin, invisible line trailing off to the right translates to massive, sprawling luxury estates occupying huge private plots. A right-skewed shape proves mathematically that the typical experience is densely clustered, while extreme wealth stretches reality outward for a tiny few. When you calculate the mean, the traditional average, its formula factors in the exact dollar value of every single property on the board. This is a number line showing housing prices. Because the mean includes everything, the sheer financial mass of those few mega mansions acts like gravity, violently dragging the mean away from the cluster of normal homes. The median takes a different approach. It ignores the dollar value entirely. It simply lines up all the homes from cheapest to most expensive and drops a 10 on the exact middle position. Because the median only cares about rank order, it's immune to the gravity of extreme outliers. It stays firmly anchored in the reality of the typical population. So, if a city government is estimating its total revenue from a property tax, it must use the mean. Those extreme mansions pay massive taxes that affect the city's bottom line. Conversely, if the city wants to determine what percentage of its population can afford housing, it must use the median. The mansions would make the city look artificially wealthier than it actually is. Choosing between the mean and the median is not about finding the correct math. It's about aligning your statistical tool with the exact real-world question you're trying to answer. Statistical skewness is not an error in your data that needs to be fixed or deleted. It is simply a mathematical reflection of a population that is highly unequal. This establishes a strict order of operations. Look at the shape of the data first, and only then choose your metric. In any environment pulled by extreme outliers, the median will always be your safest guide to the typical experience. But this introduces a new problem. What happens when we need to compare two totally different shelves, but one is measured in inches and the other in centimeters? Data is only as honest as the context we build around it. To bridge that gap, we'll need to explore normalization in Episode 7.